All right, so let us start. Remember last time I ended up with recalling what was the classification for linear maps, and we want to do similar thing for sesquilinear forms. To be more precise, Hermitian or Skew-Hermitian forms. So let me start with that. So the main important observation first is to make them diagonal forms by what is called orthogonal process. So let me recall. So this is the one of the most important theorem that one needs to use always, that is called decomposition theorem. So remember, as usual, our assumption is K is a field, and either we are assuming the conjugation is the involution is identity, and in that case we should assume that characteristic is not true, or it is K is not identity, kappa is not identity, and there is no assumption on the characteristic. All right, and also in the together case, I will keep saying phi from V cross V to K is be a Hermitian or Skew-Hermitian. Form on a finite dimensional K vector space V. And remember, in this case, then in the first case, that Hermitian should mean symmetric and skew symmetric. In the other case, we keep calling Hermitian. And the typical cases, typical examples one considers are, this is the case of real numbers, also complex numbers, this is complex numbers. Or this is a finite field, FQ, Q is not the characteristic of this field, so that means P is characteristic is an odd prime, and here you can take a quadratic extension, for example, FQ adjoin X, quadratic extension. Or you can also take arbitrary automorphism and take the fixed field of that. So there are so many examples, and even in finite field case, it is very interesting for the calculation purpose and so on. All right. So in this case, what do we want to find? Decomposition theorem says, so this is the theorem. This will help us for the classification. V has an orthogonal basis X, that we are denoting X1 to Xn. With, of course, when you say orthogonal, that is with respect to this form phi, that means phi of xij, this is 0 or I not equal to j. And therefore, why this is so important is the following. That means, in other words, we can decompose V into one-dimensional subspaces, and that decomposition is orthogonal sum. This is in the orthogonal direct sum of one-dimensional subspaces Kxi. And with phi, when you restrict to this, phi will be decomposed as orthogonal sum of phi restricted to Kxi. That means when I restrict this form phi to this Kxi, to be formed on this one-dimensional subspace. So this is exactly the same construction as probably we would have seen in the standard vector spaces with the standard forms, and they are usually called inner products. So I will not prove this because we don't have enough time. This we can state also in a matrix formulation. That says, given a matrix G, square matrix, which is Hermitian or Skew-Hermitian, then of course the same assumption holds throughout. If I would have continued, I would have continued with these together always. The same our assumption and same convention. Then what do we do? Then there exists a matrix. Then there exists a matrix A in GLIK such that with G is diagonal matrix T A G A bar. This is a diagonal matrix. Is a diagonal matrix. Such a thing you do it when you prove Jordan form also. Jordan form normally you would have proved, I suppose, for field equal to complex numbers. Am I right? Ishan?
No, so I did it for algebraically closed fields, not necessarily complex numbers.
That is complex numbers. Right, fine. Algebraically, what I mean is algebraically closed field, and that you did it because in that case minimal polynomial and characteristic polynomial have the same zeros that we mentioned. Or
no, I actually didn't use the minimal polynomial. I used that the characteristic polynomial splits. That's all.
Fine, but that also you would have used minimal polynomial implicitly because the multiplicities will also show up in the Jordan forms, no? You see, when you write Jordan forms, their multiplicities of the zeros also shows up.
Yeah,
It's not just the zeros. All right. So this the same. This is similar theorem, but we don't use algebraically closed and such thing. But that is already now we saw. No, it is hidden in many places. All right. Now this also. This I will not prove. You please see proof. See Jacobson's book. Or you can even see, I think, Lang. All right. So now I want to also recall automorphism. See, ultimately, I want to also use group actions. And all these things, as I keep saying, this originated with Jordan, and his thinking was always group actions. All right. So let me now recall automorphisms. And congruence. Congruences. All right, so we have a vector, so all vector spaces are finite dimensional. V, W, finite dimensional, over a field K. K is the arbitrary field, and as usual, I will assume my assumption, but when I need it specifically, I will state it more carefully. And I have a form phi on V. So sesquilinear form. This definition is very general. And also on the W, there is a sesquilinear form psi. So in other words, I am thinking of this V along with phi. W along with psi. So on this vector space, this is the structure that along with phi. So on the same V, there may be different phis. Fine. So these are the objects in a category, if you see. These are all right. And now, when do I call a map F from V to W? So if it is a K-linear map, these are also called sesquilinear spaces. Like you call inner product spaces. So when phi is, this is a standard inner product, then it is called inner product space. If the inner product is varying, then it's a different inner product space, like that. So this linear map is said to be compatible, or is, let us write a little bit more professional language, is a homomorphism of sesquilinear spaces. If obviously the compatibility, that means what? That means phi of xy, on the other hand psi of fx fy. These things make sense. Both are in field. They should be equal for all x, y in V. Then we call it a homomorphism. When do you call, if I write f belongs to and k v phi, this should be clear. This is a homomorphism of sesquilinear spaces from V to V in that form. Similarly, if I write ought, this is clear, right? So this is a unit group of this. See, this is again, this is a ring, if you like, or this is a monoid, and so on. But let me not go into that generality right now. So, for example, suppose you are in a standard situation where V equal to Rn and that phi equal to the standard inner product space. Then what will this condition mean? What does this condition means? That linear map preserve the distance. That distance preserving linear maps. And this ought is nothing but what we call it, Nitin's lecture he was saying, no, the distance preserving. So they're isometries.
Orthogonal group, right?
This is not orthogonal. These are the isometries. They're distance preserving maps.
Yeah, but any isometry which preserves zero is orthogonal.
Fine. So all that I am saying is this preserve the distance.
Okay.
All right. So there is a group attached to the sesquilinear forms. And then when do you say the two? So when do you say the two such objects, V and phi, V comma phi, and W comma C, when are they congruent or isomorphic? So normally the language used is congruent. Congruent. If there is an isomorphism here. All right. So similarly, this language you can convert into matrices. This is very important for a classification problem. This language. So then you will know what is doing, and then once you open up this, then there will be many other groups will open up. Like when I go on to angle preserving or some other orthogonal or special orthogonal or symplectic, all these things will come up with this depending on the form you choose it. All right, so now let us come back to classification. So this is a classification. Problem for sesquilinear forms. So again the same notation. So start with, so let me write every Hermitian respectively Skew-Hermitian form phi on finite dimensional V is congruent to the to a diagonal matrix let me write it down. This was what I was using, C1 to Cn. Moreover, the form on k power n defined by k power n cross k power n to k I will define it only for the basis elements. This is mapped to delta ijci, where of course this ei 1 to n is a standard basis and delta ij is a canonical delta. So that means this form will be congruent to the form. If I want to write more general definition of this AI, comma BI, this pair is going to summation AI BI bar CI. Bar is coming from that kappa. This is the decomposition theorem. I just wrote it in the language that is suitable for us. So this is the first step, of course. Now, this is, if you take arbitrary field, even for Q or even for a finite field, the classification is not as easy as, of course, the linear maps. But for complex numbers, it is easy because again, C is algebraically closed. And in that case, I will write the corollary then. Right? What did we actually more than that? What I need to assume is the field is quadratically closed. Then it's easier. Now, what does one mean by quadratically closed? That should mean that if I take, so what I will need is the following. See, everything is connected to the unit group, K, unit group of the field, K cross. What plays important role is the following. If I look at norm 1 units, so what is this? This is by definition. They are all those A bar. where A is varying in the unit group. This is a subgroup of K cross. This is a subgroup. And as you know, this is K prime is a fixed field. This is a fixed field of that kappa. And actually this unit, this is norm 1 unit group. And this is a unit group. This is we keep calling it a unit group of K. And actually this NK cross is actually contained in K prime. You see, when you apply kappa to this, they are invariant. So therefore, this is actually contained in K prime cross. They are non-zero, of course. So and actually you can say actually can describe this group. This group is nothing but, I will write 2 on this side. I did it earlier also, this notation. This is K cross. This is the subgroup of quadratic units. In K cross. And the results are better when this subgroup NK cross is actually K prime cross. See, this is in general inclusion only, but if it is equal, then it is the results are easier to prove. And that's what exactly happens. This happens, for example, when K equal to C. Therefore, we can write it more easily for C. That I will write it as a corollary. So, K field and as usual assumption. And in addition to that, with K equal to 2K. And this assumption is satisfied, for example, K is algebraically closed. Everybody has a square root. Then all Hermitian. Now let me write in terms of matrices. Matrices in MNK of equal rank are congruent. And are congruent, and the diagonal matrices all zeros, that means zero matrix. Then diagonal matrices 1 here and remaining zeros, and then 2 at a time, three at a time, and so on, and then diag all ones. So this is rank 0, rank 1, rank 2, rank n. This form a complete representative system for congruence classes of Hermitian matrices. This is very easy. You just have to tie up, and this goes in similar with what we saw it in a linear maps. The theorem is easier, Jordan form is easier when you assume the field is algebraically closed. That is because you need characteristic polynomial and minimal polynomial should split into linear factors over C. All right. Now you may ask what happens if this assumption is not there. Then obviously the problem is more complicated, and then one need to study values of the quadratic forms which are associated with sesquilinear forms. And that topic we are not going into it because we have no enough time. It is not difficult, but we are lack of time. All right. Now the next is now little bit finer, more classification. In case of the field is real numbers, this is not included there because this assumption will not be satisfied for real numbers. It's not closed under quadratic. Its square roots are not there for all real numbers. So therefore we need little bit different or a little bit more finer. So I don't know whether you guys have proved Jordan form for real numbers. Have you? Sonakshi?
Yes, sir. Yes, sir.
Have you done Jordan form for real numbers?
Yes, sir.
What is it?
Sir, we define some maps from the vector spaces and then take their direct sum and when they are invariant, and then from there we get the Jordan form.
But Sonakshi, one difficulty would be definitely when you take a linear map, it may not have a real eigenvalue.
Yes, sir.
And then what do you do?
Sir, I don't remember.
So I
the
think
assumption is made that the eigenvalues are in the field. So when it is over here, we make the assumption that the eigenvalues are in the field K, and then we proceed.
yes.
That's what we are asking.
But that means you go to complex numbers and do the Jordan form there. See, the problem
Yes.
the problem is the following. When, for example, you people have studied differential equations and you are looking for a solutions of the differential equations of a real functions, then you need also the real functions you need. So one has to be little careful. But in this case, it can be done. But you have to go to complex numbers and do it, and again come back to real numbers by getting rid of that bar. And so the Jordan blocks will also involve 2 by 2 blocks with a negative determinant. All right, so the block will, you remember, the block will correspond to negative determinant. So that normally at the end that is ignored in the university I don't know, but real problem is there also. So one has to go back and review it more carefully. So now similarly, I am going to attach. So this is now for typically for this pair now. I will assume now my notation will be this double line K. Either it is a field of real numbers or complex numbers. And I want to do finer. I want to attach some more invariants to Hermitian forms. And I want to classify them in terms of those invariants. So the typical two invariants are, what are they called? Type and signature. Of these invariants, I am defining it for of Hermitian forms on k vector spaces. V and of course finite dimension. And when the field is real numbers, Hermitian should mean symmetry. And when K is C, it should mean Hermitian, the conjugate. And of course, why this is together is better to call this. Again and again I am saying, why is it better? Because even in this complex case, there is a symmetric case. In this, there are two cases, symmetric and Hermitian case. All right, so that is the advantage of that notation. And characteristic to assumption is already satisfied, so we don't have to worry about that. All right, and now in this case, another good thing is we know the Galois group. Galois group of C over R has only two elements, namely identity and kappa. And as I said earlier also, even this, it involves equations. It involves the zeros. So not that this is a pure linear algebra, no. It also involves zeros of the polynomials and field extensions and so on. All right. So what does the classification theorem says? Classification theorem, what we wrote above, that shows that if I have any Hermitian form on a finite dimensional, either real or complex vector space, then you can find an orthogonal basis with respect to that form such that the Grams matrix G phi of that basis will be congruent to, this is congruent to the matrix, to the diagonal matrix of this form, diag 1 1 1 1 1 so many times, minus 1 minus 1 minus 1 so many times, and 0 0 0 so many times. Now why this? Because you see, this will correspond to the positive real numbers and this will correspond to the negative real numbers, because we can get rid of that square. So this is, so this one and this one, that are good invariant. Those, this is P, this is Q, number of minus ones is Q, and now number of zeros is therefore N minus P plus Q. And also P plus Q is the rank of that form. See, I started with Hermitian form phi. That is what it says. You see here, it says that we can make it, this is for complex numbers, but if it is not complex numbers, what? Then we can make it a diagonal matrix. That is what we wrote it, diagonal matrix. And in this diagonal matrix, some are positive, some are negatives, and some are zero. The positive ones, I will write them as squares and then do that congruent operation, and then we will get rid of that and make it 1. Similarly, the negative ones, I will write them as minus of a square and then again do the same congruence. So that will make it to be minus 2. Are clear? So these two integers p and q are very important because their addition also gives the rank. So non-degenerate will means p plus q is the whole n. So that will be non-degenerate means. All right, so therefore the definition, I make the following definition. Definition. With that notation, and phi is our form from V cross V to K. Either it is Hermitian, either K is R or C. Then, first of all, note that these P and Q, these also I will mention it below, P and Q are uniquely determined. So phi is non-degenerate. If and only if p plus q is n. Otherwise, p plus q is a rank. All right, now we know it is called phi is called positive definite. If phi xx is bigger than 0 for all x in V, x non-zero is positive definite. Negative definite, if p xx is negative for all x in V, x non-zero. I should have also added positive semi-definite. That is when you allow the equality here. Similarly, negative semi-definite. When you allow the equality here. Otherwise, we call it indefinite. If there is x with this is positive and there is x with this is negative. So let me call that as y. For some x in V, for some y in V. All right, now what does this matrix is also denoted by, let us denote it because it will save a lot of time for me to write here. This matrix, this diagonal matrix is also denoted by E n pq. The number of ones is p, number of minus ones is q on the diagonal, and that n is the size of the matrix. Yes. So what is p now? Is in the this is the Sylvester's law. This is Sylvester's law of inertia. That any Hermitian form on K vector space V, finite dimension always, and if I have a orthogonal basis X, orthogonal basis X of V with respect to phi, such that the Grams matrix is the diagonal matrix. So what do I write sentence? I will write equal to E P Q N. Then P equal to the maximum. Okay, let me write again in the notation so that I will save some time. So this is the maximum of dimensions of subspace V. So W is a subspace of V and such that phi restricted to W is positive definite. And Q is max dimension K W prime. W prime is a subspace of V such that phi restricted to W prime is negative definite. In particular, what I want to say that P and Q does not depend on the special choice of the orthogonal basis that one chooses. So let me record in particular. P and Q do not depend on the choice of the orthogonal basis X of V. So this gives us a definition. This again, I don't have time to go. This again gives us a definition. The pair PQ is called the type of phi. P is called inertia index. Everything of phi. And the integer P minus Q P minus Q is called signature of phi. And Q is also, you can say Q is called the Morse index. Morse index of phi. And of course, I must write here, I must mention here that I've seen a lot of papers written by computer scientists who uses this type and signature of a quadratic form to count the number of real points on the algebraic varieties. So that this computation of P and Q is very important. How does one compute P and Q? See, always this is a theory, but when the problem comes, how does one compute and how is it related to the zero? How is it related to the zeros of course, characteristic polynomial and so on, because matrices are involved. And actually, the oldest calculation will go back to Descartes' rule of sign. Again, one has to be very well equipped with the theory of equations, which was the older subject. And Jordan brought this because he wanted to do theory of equations. All right. So that Hurwitz criterion will tell us how does one compute P and Q effectively. So I will state it, and with that I will end my lecture and the whole course. So this is Hurwitz criterion. Phi, as usual, Hermitian form on K vector space V, finite dimensional. And again, remember the case of symmetric bilinear form over R is included. Case of symmetric bilinear form over C is included, and case of pure Hermitian, that is complex Hermitian, is also included. And suppose X is a basis. K basis of V. Then we know that this form phi is determined completely by the values on a basis that we have seen. And now I am writing the principal minors of that Grams matrix. So let the principal minors of Grams matrix of phi with respect to this basis be. So I am going to start with D0. That is, this is by definition 1. Zeroth minor if you want. Di is the determinant of the first I by I rows and first I columns. That is phi x1 goes up to phi xi. No, x1 xi, first row, then second row phi x2 x1 phi x2 xi, And the last one will be phi xi x1, phi xi xi. The determinant of this. So, in general, if you have a matrix, this is the first minor, 1 cross 1, then 2 cross 2, then 3 cross 3, and so on. So these are called the principal minors, the determinants of these matrices. And they are how many in number now? I equal to 1 to n. And D0 I have already denoted by S. So what do the criterion say? And the assumption I am making is, so let the principal minors of the grounds matrix be D0 and all we assume all DIs are non-zero. No. What I'm all non-zero. Sorry, all I'm assuming all of them are non-zero. Then this is very important connection with the theory of equation. Then the type of phi is the pair n minus q, comma q. See, remember the assumption is Dn is non-zero, that means it is non-degenerate case. And the type is this, where q is the number of sign changes in the sequence D0, D1, D2 up to Dn. So you say if they are different sign, then you count it once. If they same sign, discard and so on. So the number of sign changes in the sequence is precisely that integer q. And that is the criterion. So once you know q, once you know it is non-degenerate, then you know what the p is. So in particular, you can write down when it is positive definite. You can also write down when it is negative definite. Positive definite if and only if, so corollary would be phi is positive definite if and only if all DIs are positive. Negative definite if and only if minus 1 power I DI are positive for every I. This is for every I. So negative definite means at every stage there is sign change. And positive definite means either they are throughout positive or throughout negative, no sign change. And if you see the proof will depend on what is classical theorem, what one learns in theory of equation, the Descartes rules for sign. So I will not go more into details and then I will stop here. I will end my course.